Now that we are done with the initial data analysis, we can start to model our data with some statistical modeling. And we are going to start with the simple regression model where we have one x variable and one y variable. And we are using the information in the x variable to explain the variation in the y variable. And in order to do this, we're going to use the stats models module in Python. So we have to import statsmodels.api as sm, like stats models. If we run this, well, we get no module named stats models. Okay, so then we can go to the terminal here and we can write py.m pip install and stats models. We can either run it here, or we can run it in the command prompt here in our command prompt window. So let's do that. And we see that the stats models module, it's downloaded and it's installing the package. And we see that it was successfully installed. Then we can go back here and run this cell again, just shift enter. And we see that we can import statsmodels.api. What we need to do now is to define our y variable and our x variable. So we just define our y as our price and the x variable as the square meters, because we saw that the square meters and the price were slightly positively correlated with 0.36. So that would be our first guess, that larger, our initial hypothesis is that larger apartments would cost more money or incur a higher price. The problem here is that the OLS function in stats models, it does not add a constant or an intercept term automatically, which means that we have to use the sm.addConstant function to our data. And if we just run this, and we can see what is contained in x, we see now that we have a constant term in addition to the square meters information. So now we can, for example, put our information into something we call regsim, and we use the OLS function from the stats models package, and we provide the y variable, the x variable. So now we have defined that this is an OLS model with our y variable and x variable. But in order to get the coefficients and such, we have to fit the model to the data. So now we can just hit enter on that. And if we print the regsim, we see that this is an object which means that we have to use another method, the summary method, to actually see the output. So here we can see that we have the r squared, which is often interpreted as the percentage of the variation in y, which is explained by the variation in the x variable. And we also can interpret this in a simple regression model as the squared of the correlation. So if you take the square root of this, you should get the correlation between x and y. This is only for simple regression models. And here, with the coefficients, we can see that the constant is 2.7 times 10 to the power 6, which means 2.7 million. And the square meters is 2.1 times 10 to the power 4. So we just move the decimal separator here 4 places, which means that this is 21,000. So for each square meter, you add on the apartment, you add on about 21,000 kroners to the price. If you want to interpret the significance of these coefficients, you can look at the p-value, and the p-value is interpreted as the probability of getting a more extreme result away from 0 than this coefficient value, given the standard error. So here we see that we reject the null hypothesis that the constant term is equal to 0, because the p-value is less than 0.05, which is a common cutoff. But we can see here that the p-value for the square meters, it's above 0.05, it's at 0.1, which means that if we use 0.05 as a cutoff, then we do not reject the null hypothesis that this the coefficient on square meters might be 0. So what we can do now is that we can also look at the residuals. So in our regsim object, we also store the residuals. So we make another variable, regsim residuals, and here we have the resid or residuals. So if we just print the residuals here, we see that how much our model is off compared to the true value. So in this case, we miss by 416,000. In this case, we miss out, or our model misses the true value by 1.14 million, and so on. So that's quite nice to know. And we can plot the residuals as well. And figure axis subplots as usual, x dot and we can plot the residuals, and we would like to plot it with some dots, and here we go. And what you could do also is to, well, here you cannot really see a pattern other than the first 10 observations. You know that they are for Oslo, and the last 10 observations, you know that they are for Trondheim. And if you draw a line at 0 here, you see that most of the Oslo apartments, they are above, they have a positive residual because the actual value minus the model estimated value is positive. So the residual is positive, whereas the opposite is actually the case for the Trondheim apartments. This makes the case for maybe adding some other information into the model, like making a multivariate regression. Or we can also check whether or not we can capture some non-linearities. So for example, if you had plotted the price versus the square root, square meters, and you had like this non-linear exponential pattern, you could make a non-linear model. For example, a logarithm versus logarithm model. So let's do that. We can have a new x variable, and we make use of the numpy log function. And we have square meters. And x equals stats models dot add constant. We just put in x. And then we have the y variable is equal to the logarithmic transform of the price. And we can make these logarithmic transforms only with variables which are positive. So for example, we can expect that the square meters is always positive for traded apartments, and the price is also always positive for traded apartments. So now we can fit our model. So reg sim and log it should be, and we use stats models, well, s. Almost wrote it quite wrongly there. We provide the y variable and the x variable, and we run the fit method immediately. So now we have fitted the nonlinear model, and we see here in our variable explorer that we have the regsim log here. We can run a summary on that, and we see that, well, the r squared is a bit higher, but since the y variable is not identical between the two models, you cannot compare the r squared values. We also see that the constant term and the square meters, they are now very different because we have the logarithmic transform of the x variable and the y variable on each side of our equation, what we can see is that we have a slightly significant value of the square meters coefficient here. So we tend to reject the null hypothesis that this slope on square meters is actually equal to 0. As a last exercise, we can add the square, or we can have price on as the y variable and try to explain the variation in price by the square of the square meters, the size of the apartment. So then we can have x equals to np dot square, because we use the square function from the NumPy library or module, and we are squaring this square meters variable. And of course we have to add a constant to this, and y is now ordinary data and price. So if we run that, we now have a new data set to work with, and regsim square is now our new container for the output from the ordinary least squares, y, x, and then fit. And immediately we would like to see the summary of this this model. And we see that the r squared has gone down. Often you would add the linear term of the squared variable as well. This was just to show you how you can work with squared variables as well.